Okay, right. So these two magnetic moment, they interact. Now we can model it. We can try to explain why that's the case. So using a sort of fairly close analogy to classical mechanics. Now, well, pretty well everybody imagines the atom, pictures the atom as a nucleus in the center and electrons whizzing around the nucleus, right? Like this is the nucleus, and you've got electrons whizzing around it. Okay. Now that's one point of view. Now, analogously, you could have my fingers here as the sun, and the Earth is orbiting the sun. Okay. Now, for thousands of years, people believed that the sun went around the Earth because it's such a common sense notion. You just have to look out the window, as I'm doing right now, and the sun is going down. I'm running out of light. The sun goes around the Earth, right? That's just a common sense notion. So it's just from which perspective you're looking at it. Now, you could look at from the sun point of view, like if you're positioned outside the solar system, well above the plane of the solar system, the planets orbiting the sun, then it will appear to you as though the planets are orbiting the sun. The Earth goes around the sun. Now, from the point of view, by analogy, from the point of view of the electron, it looks as though the nucleus is orbiting the electron, right? From the electron's point of view. So that means now the nucleus is charged. It has let's say it has Z protons in the nucleus. So it will have a charge of Ze, where E is the magnitude of the charge on the electron. So the magnitude of the charge on the proton is equal to the magnitude of the charge on the electron, which is different signs, different types of charge. Opposite charges, positive and negative charges, attract each other, and like charges, both positive or both negative, repel each other. You've probably known that from high school physics. Okay, so from the point of view of the electron, the proton is, well, the nucleus is whizzing around the electron. Like here's the electron. Now, from the point of view of the electron, so the nucleus is whizzing around. It has a charge of Ze, right? Where E here is the charge in the electron, its magnitude. So Z will be positive integer. Okay, so so from the point of view of that electron here, where my finger is, and you've got this Ze charged nucleus whizzing around. It's from the point of the electron. That whizzing nucleus is generating a current, right? A current I. Now, why is that? Well, what is current? By definition, what is current? It's the rate at which charge passes per second. How much charge passes a given point, if you like, per second. So imagine here's where the electron is, let's say, and so at the tip of this black felt tip pen, so just here. Let that be your reference point, and here is just here's a circle of radius r here. Okay, so if this nucleus is whizzing around in a circle at speed v here, then how much current is from the point of view of the electron? What's the current of this charge? From this point just here, how much charge passes that point per second? Right? That's the definition of current. The amount of charge passing a point, like flowing down a wire, for example. Well, yeah. Imagine, by analogy, imagine you've got a circular wire, let's say, and this nucleus is sort of whizzing around the wire. Imagine. So what's the current in the wire? How much charge is passing that point in the wire per second? Well, the circumference of the wire is 2 pi the radius, right? 2 pi r. That's where this comes from. 2 pi r. So if the velocity of this nucleus is v, it will pass this point per second. So if the velocity is v, it will travel distance v in 1 second. Let's say this is units of length per second. So how many loops? Like, what's the frequency? How many times does that charge of ZE pass this reference point here per second? Well, it'll be the number of loops it does of this circle per second, right? Which is v divided by the circumference, right? So so this v divided by 2 pi r. That's the number of loops it does, and so the charge is ZE, and that charge is whizzing around. So the amount of charge flowing past that point per second will be ZE times this, right, the frequency. So that's your current, okay? From the point of view of the electron, that's the current of generated by the nucleus, in a sense. Okay, now give you a little bit of history. I assume you've done some electromagnetic theory. If not, imagine this pen now is a wire connected up to a battery, and you connect the wires to the battery, and then suddenly current flows through the wire. Okay? In other words, electrons just flow down the wire. That's what current is, effectively. All right. Now, early 1800s, I think. Not too sure. I need to refresh my memory with an electromagnetic textbook. And by the way, I have to do a course on that, undergrad level course on electromagnetic theory. Either a course or a mini course. It keeps cropping up. Okay, now imagine with this hand here, I have a compass, a little compass with compass needle. And you switch on the, and say bring the compass needle, or say here, so close to the wire. And then I switch on the, I connect the wire to the battery, and then current flows, electricity flows down the wire. And then the needle on the compass will wiggle, it'll be perturbed, it'll be jolted as the current switches on and off. When it switches on, the current needle will spin, it'll be disturbed. And now when that was observed for the first time, it caused a sensation, because prior to that observation, electricity, the two phenomena, plural, that's the point, the two phenomena of electricity and magnetism were just totally separated in people's minds, in physicists' minds. They just had no inkling that they were connected in any sense. But this experiment shows clearly that there is a connection, right? That electricity and magnetism are linked somehow, because you've got electricity flowing down the wire, and as soon as the flow starts or stops, the needle in the compass gets disturbed. It starts spinning. So that shocked physicists, and they realised then that somehow, in some vague, unknown, curious, fascinating sense, somehow electricity and magnetism were linked, and that just opened up a whole new domain of research, inspired Faraday to go investigating just what was that link, and out of that came the electric motor and the dynamo, and out of that came the 20th century technology. And I mean, imagine life without electricity, right? So you can, in a sense, you could start anywhere in the history, but that phenomenon, the spinning, disturbed compass, when you switch on or off the electric flow in the wire, it seems such an innocent little phenomenon, but look what it led to. Just amazing. I mean, basic science eventually leads to new technologies which just have revolutionized our lives. So, fundamental research is absolutely critical and basic. So when the Americans, for example, cut the funding of the superconducting super collider, which, if it had been built, would have been more powerful than the LHC, Europe's Large Hadron Collider. That was a tragedy, because now America's particle physicists have migrated effectively to Europe. So it's now Europe getting all the world publicity and the limelight. That to me was symbolic.